Okay. Hello and welcome to week 8 of problem solving session for NPTEL course Introduction to Operating System. And this week is dedicated to security of operating system. And so we have a couple of quiz type questions here in this session related to the topics that you have learned in this week, different kind of attacks and access control mechanisms. So let us get started with the quiz. So the problem one here is that ASLR, which is address space layout randomization, randomizes the position of all variables in the stack and thereby making it difficult to perform buffer overflows. Is it true or false? Okay. Any other answer? Okay, let us quickly look at ASLR. Okay, anyways, I think this picture here. So, okay, the answer to this problem here is false. So it doesn't randomize the position of all the variables in the stack. It just randomizes the location of different program segments, like where the stack is starting, where the library code is located, heap is located, program code is located, and in the stack also where the different frames are located. Like it can add arbitrary amount of uh, gap between the different frames, and so it randomizes the location of these different kind of program segments, but it does not randomize the individual elements of the stack like variables. And the way ASLR is able to prevent, say, ROP attacks is because when you have randomized the, say, you have added some arbitrary amount of uh, space between the different uh, activation records or the different function frames in the stack, then it becomes hard for the attacker to locate exactly where the return address is located. So because in a ROP attack, the attacker tries to change the return addresses so as to stitch the gadgets, right? So by changing these stack addresses, like where the stack is located, where different function records are located, it becomes hard for the attacker to find the exact location where the return address is located and also the exact location where it wants to jump to. So it randomizes the address space, and but it does not randomize the position of individual variables in the stack. No, variables are not randomized. So like in your, yeah, so like this is your one stack, this is your stack, and so this return address is here. So the attacker will try to say there are locals of this function. The locals of this function can be a buffer. So when the attacker does a buffer overflow attack, that can lead to change in the so that it can change the return address. Now, but if you uh, now maybe it is able to change the return address, but where to point the return address, the correct address is, it won't be able to compute that correctly with ASLR because you have randomized the locations of different segments of the program. Like maybe you have a gap here between the blue region and the green region. If you add an arbitrary amount of space which the attacker is not aware of, then you will not know exactly, the attacker will not be able to know exactly where to jump to, where to return, where is the another function is located. So the program segment is also randomized. So it will not know exactly where the code is located. So the return addresses here will not, it won't be able to get those return addresses. But these variables, the locals of the function, the variables, they are not randomized. They will be as it is. Only the program elements, like the, as this picture shows. So it is possible that earlier this was how your program segments were, like different components of your program, stack, library, etc. After that, it randomized it. So the program is now moved to some other address in your address space, and library code is moved somewhere else. So it becomes hard for the attacker to compute these addresses, like where to jump. That the jump location is a location in the code, right? Jump to some location, it's an address in the code. Now if it doesn't know where the program code is located, then how can it find where to jump? So it becomes hard for the attacker to find exactly where to jump, but it doesn't randomize the variables on the stack. Not variables. Yeah. Oh, by variables, I think it means the when the variables are in the stack. So when the memory is located for a variable in the stack, it's not, yeah, yeah, they're not randomized. Yes, 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 that is correct. The code is moving different locations, but when the code is run at runtime, the stack is the image, right, of the program. So at runtime, locations memory is allocated for each variable on the stack. So the question is asking for the position of those variables. Let's say there are two variables A and B in main, and when you create a stack frame for the main here, you will add parameters here for main, like variable A, variable B. So question is saying, are those randomized too? Like maybe variable B will become first, then variable A will come second, or variable A comes first and variable B comes second. That is not done. Like it's not that fine grained. Okay. Okay. Any other question? Okay. Okay, so the next problem is a match the following question. It has four options, and gadgets, canaries, shellcode, and ASLR, and you have to match them to these four options. And I'll give you some time to look at the statements, and then you can choose one of the following. So any answers? Yeah. Okay. So ASLR prevents ROP attacks. Okay. Hmm. Okay. So, but does the other uh, options also match? Okay. Okay, so in ROP, return-oriented programming, a type of attacks, you must have learned about something called gadgets. So what is gadget? Gadget is as the description here says, it's a short sequence of instructions ending in a return. Okay, and I don't know if it's here in these slides. Yeah, so gadgets and some useful instructions, they're ending with a return, and like there could be a lot of instructions like that. Of course, in your program, every function is ending in a return instruction. And so what the attacker can do is that it can change these return addresses on the stack so that it will return. Like for example, this is your gadget 1 here. The return address here, if on the stack, when this is changed such that now it jumps to gadget 2. Now at the end of the gadget 2, it changes the return address to gadget 3 and then gadget 4. So in this manner, it will be able to execute this sequence of instructions like move L ESI, comma 0x8 ESI, then after that this instruction, then this instruction, this instruction. So even though this sequence of instruction was not originally part of your program, the attacker is able to execute this sequence of instructions by stitching together these gadgets. Okay, and so these, what is gadget? It's a short sequence of instructions ending in a return, that is gadget, and this is called return oriented programming because you're using return instructions here to arbitrarily do some computation which is not originally part of the program. Then second here is canaries. So what is a canary? Canary is a pseudo random number which detects buffer overflow. So it's a, yeah, so it's a canary. So canary is that in arbitrarily at some locations in your uh, program, in your on your stack, you're going to add some random numbers like pseudo random numbers. Pseudo means they are not actually random, but they're just, but they look like random numbers. So they are added, you add some random numbers, okay, which cannot be easily guessed. And so the attacker, if it say does a buffer overflow attack, say in buffer 1, and tries to change this return address over here, then in that process the attacker would have changed, because the buffer overflow means you have started writing from here in this buffer and you're writing till the return address. So the attacker would have changed this canary here as well, and when that canary is changed, it is detected by the program, some code which is over there which is checking this which is checking whether the canary is corrupted or not. So if the canary get corrupted, that means a buffer overflow attack has happened. Okay, so there is some code which is inserting a canary, and it is also checking if the canary has got modified or not. So that's canary. Then shell code. So some um, shell code you can. So for this, the option here which is matching is third, which is the shell code can be executed in the stack if the bit, a non-executable bit is disabled. So by default, uh, on so a W XOR X, which is write XOR execute, but it's a security mechanism which is enabled in your program, which means that if the data pages in your program are only writable and not executable, which includes the stack and the heap. Okay, and the executable pages in the program, which is the code pages, they are not writable, so the attacker cannot. And that this security mechanism ensures that the attacker cannot add any arbitrary code, any new code basically in the code pages, because it cannot write the code pages, so it cannot add any new code in the code pages, and it cannot write any, it cannot execute anything from the data pages, which is your stack. So for that, this non-execute bit, which is non-executable bit, it is set in the stack, in the stack pages, in your page tables. Okay, your page table have this page table permission bits, right? So in that there is a bit non-executable bit. So the non-executable bit is just saying that this page is not executable. It cannot be executed. So in order to execute the stack, the attacker can change this non-executable bit, so making the stack executable, and then it can, using a buffer overflow attack, it can write some code in that stack and a shell script, and then it can jump to that location using, by changing say the return address, jump to that location, and then the code will be executed. Okay, and ASLR, as we have already seen, address space layout randomization, which randomizes the different code segments, code components like library code, program code, stack, heap locations in the address space. That is one of the prevention mechanisms for ROP attacks, because if your code has been moved from to a different arbitrary or a randomized location, then it becomes hard for the attacker to guess where exactly the code is located, where it wants to, which it wants to, like basically it becomes hard for the attacker to guess the location of different gadgets in the program. So it helps prevent ROP attacks, but you should also know that ASLR can be defeated. Like, it is not a foolproof solution to ROP attacks because it's just randomization, and if the attacker is able to find out in some way where the program segment is located or how it has been randomized, then this mechanism is defeated. So it is not like a foolproof solution, but it does help. And ASLR and stack canaries, these and WXOR X, these are some of the defense mechanisms which are enabled in most of the computer systems, your desktop systems, PCs, etc. by default. Okay, because they do not cause, or they do not lead to a lot of overhead in your programs, so they do not cause a lot of program that performance overhead, and that is why these type of these canaries, ASLR and also WXOR X defense mechanisms are enabled by default in your systems. Okay. Is there any doubt? Okay, so if not, then let's look at the next question, which is, I think, quite related. How does the non-executable NX bit, X we read for executable, non-executable bit prevent buffer overflow attacks? I think I've already explained that, but okay, options here are A, it prevents buffers from overflowing. B, it prevents certain code from executing in data segments. C, it prevents the return address in the stack being replaced by an arbitrary location. And D, all of the above. I think I've already answered this question, but I would ask you to still like try and answer it. Okay, yeah. Yes, that is right. So option B here is right. The NX bit, no non-executable bit, if you disable it, that is, you set it to 0, then uh, then buffer overflow attack can happen. But the question is, how does it prevent the buffer overflow attack? So it prevents certain code from executing in data segments. Yeah, so in the data segments, if you set the NX bit, that means the data segment is not executable. So the attacker cannot execute any which data in the data segments. Option A is incorrect here. It doesn't prevent the buffer from overflowing. Okay, so the buffer can still overflow. It doesn't prevent that. And so NX, it doesn't prevent the buffers from overflowing. It only prevents the attacker from executing some code in the data segments. That's all. Okay. It doesn't prevent the buffer from overflowing, and hence it doesn't prevent the return address in the stack also from being replaced by an arbitrary location. So it only prevents the attacker from executing the data segment. That's all. Okay. Next problem is, an ROP attack can potentially be detected at runtime by A. Canaries, B. The number of return statements executed in the processor, C. The number of return statements present in the executable, and D. By a non-executable stack. Any answers? Okay. Yeah, so there are two answers which are stack canaries. Yeah, so yeah, if stack canary is mechanism is enabled, then definitely if the stack canary is placed in such a manner that it will be before, as we had seen here, if it's placed here like this, then the stack canary will be changed whenever the attacker tries to change the return addresses, and therefore it will be detected. See here, so option number one here is option A, canaries, is right. So an ROP attack can potentially be detected at runtime by canaries. Okay. Okay, so the next problem is in Bell-LaPadula model, a user with security clearance confidential can read top secret file. True or false? Any answer? True. Okay, can you try again? Okay, let us look at the Bell-LaPadula slides here. So the mandatory access control here, uh, we have this multi-level security policy that is for every object in your system. You have a classification level, that these four classes here, whether this object or whether that is the object can be a file, if it is unclassified, confidential, secret, or top secret, and subjects, which are your users, have a clearance level, which are also these four values: unclassified, confidential, secret, and top secret. So a subject with X clearance can access all objects in X and below, but not vice versa. So the information only flows upward and cannot flow downwards. That's mandatory access control. And in Bell-LaPadula model, we have two properties here. The first one is no read up and second one is no write down. So the question is asking you about the read property here. So let's look at that. So if there is a user, if the user's clearance level is confidential, then the user can read the files which are marked as confidential. It can read the files which are below, that is marked as unclassified, but the user cannot read any file which is secret or top secret. That is the file for which the classification level is more than confidential. Those files or objects cannot be read by the user with clearance level confidential. So there is no read up. You cannot read up above your classification level. Okay. So the question here is saying a user with security clearance confidential can read top secret file. Is it true or false in Bell LaPadula model? Yeah, so it is false because in Bell LaPadula, as I just said, if the clearance level is confidential, then it cannot read top secret objects. So it cannot read that. Okay, next question is in Bell LaPadula model, a user with security clearance confidential can write top secret file. Is it true or false? Okay, okay. True, false. Okay, there are two answers, true and false both. Okay, so it is, I hope it is clear that the policy says no read up. So you cannot read above your security clearance level. Okay. So if the clearance level of user is confidential, then the user cannot read files with classification level above confidential, that is secret and top secret files cannot be read. Okay. But then the Bella Padula model says that other policy is no write down. So if your clearance level is confidential, then you can write to the files which are confidential, which are secret, and which are top secret. So you can write to all of these files which are at your security clearance level or above your security clearance level, but you cannot write down. Okay, so you cannot write here. So question here is saying that a user with security clearance confidential can write top secret file. Yes, it is true. So it can write to top secret file, but it cannot read top secret file. Okay, so user with say security clearance confidential is allowed to write to a top secret file, but it is not allowed to read a top secret file. And why is it not allowed to read a top secret file? For that, we have, or why it is not allowed to, yeah. So first, let's understand why no write down. Why is it not allowed to write down? It's both are related. So if your uh, if this is your process or your user with confidential clearance, then the user can read these files. No, sorry. Then it can read the confidential file. Okay, yeah. So if the process has confidential clearance, then it can read the confidential file. Okay. Then after that, if it is allowed to write to unclassified, then it is possible that there is some part of this process, let's say, which is some malicious code, then it can write this to some other arbitrary, to some like unclassified uh, user or some unclassified program, which is it can leak that data by if it can read some confidential data and then it can leak it if the write down is allowed, because it would then have the permission to write it to some other unclassified user. But since Bell LaPadula does not allow write down, so it is not possible in Bell-LaPadula model. So in Bell-LaPadula model, this arrow here, this flow is not allowed. So write to a lower level is not allowed. So even if the process here has confidential clearance, it can read the confidential data, but the process, even a malicious code inside the process will not be able to leak this information to a lower clearance level because this flow is not allowed. No write down is allowed in Bell-LaPadula model. So that is why we have no write down, so that a, a secret data or the confidential data is not leaked outside the uh, outside. That's all. So no write down. So you cannot leak. So it prevents the confidentiality of the objects, but the it doesn't prevent the integrity, because if this user is say, or if this process here is, let's say this trojan is there, which is a malicious code. So since this process has confidential clearance, it can write to all of these other objects which are top secret, secret and confidential. It can write all these objects. So the trojan here basically can modify these top secret, secret, confidential. It cannot read what the top secret is because no read up, so it cannot read what it is, but it can just write it. It can write some arbitrary data here. So it can basically breach the integrity of the system, like it can modify the files. So your data might be lost or data might be changed. But so Bell-LaPadula model here achieves confidentiality, that is the data is not leaked outside because it here has this because of the no write down policy, but it doesn't achieve integrity because of the uh, same policy, because it can write to all the above objects. Okay, is there any question? Yeah, reading is not allowed because you want to achieve confidentiality. So you don't want let's say, a unclassified user to read a top secret. But an unclassified user may want to send some information to top secret, say user. So it is able to send some information to the top secret users here by writing somewhere, and you wanted to write only in somewhere in the top secret directory, because otherwise the data can be, if you write it somewhere in unclassified, then it can be read by others also. So in this way, yeah, your question is like it cannot read, but it can write. Yeah, so it is not allowed to read because we want to achieve confidentiality. If it can read, then it can read the top secret data. And we allow it to write because we want to give the user uh, like access, like if it wants to share any data to the top secret users, say, so that it can write that. Yeah. Okay. Yeah. Yeah. If there is any other question, you can unmute yourself. Ankush, you can unmute yourself and ask, or you can write in the chat box. Okay. I'll wait for you to ask your question, and then, but still, let's look at the next problem till then. Okay, problem 7 is programmer X has found that the, sorry, Okay, programmer X has found that the source code has a buffer overflow vulnerability caused by string copy instruction. He then used strncopy in place of strcpy to prevent buffer overflow vulnerabilities. Which of the following is true? First is buffer overflow vulnerabilities caused due to strcopy is avoided due to bounds check. Second, this will not make any changes in the source code. Third, buffer overflow attack will not occur in the source code. And D, none of the above. So can anyone tell me how does strcopy function uh, is vulnerable to buffer overflow attack? Hmm. Yeah, yes, yes. So any data which is stored after 4 bytes will be overwritten. Yeah, yeah. So that is right. Okay, thanks for answering. Yeah, so it just takes one more parameter, which is n here, which is the number of bytes that you want to copy. And then in the function strncopy, it also makes a check on the number of bytes which are being copied. If that is less, if that is greater than the size of the destination buffer, then it won't, like basically it will copy only the number of bytes. uh, so say as you gave the example, your destination buffer is only of 4 bytes, then it will copy only 4 bytes. Yeah, I did that. Yeah, it will prevent. Okay. Yeah, so here the answer is option A. Buffer overflow vulnerability caused by str copy is avoided due to bounds check, because in the string copy, string n uh, function, it copies basically n bytes from the source buffer to the destination buffer. So if the n bytes are less than the size of the destination, then it just copies those n bytes and then pad it with, say, null in the rest of the, uh, if the destination buffer size is more, then it just copies first n bytes and then rest are set to null. But if your number of bytes that you're trying to copy from the source to the destination is more than the size of the destination, then it does a bound check. It checks that the location, how many bytes are available, and Therefore, it due to that bound check, it is able to prevent the buffer overflow attack because it will not allow you to copy more than the space which is available in the destination buffer. Is there any question? Okay. True or false? Number of gadgets present in the implementation depends on the number of C3 instructions in the machine code. So is this question from the assignment? From the current assignment? Week 8? Okay. Is there any, do you have any doubt in this question? If you have any, if you're asking me for answer, then, but for the week 8, you have to, so, yeah, but it's an assignment question, so I cannot answer it. Yeah, so I am, yeah, I also don't know what a C3 instruction is. Actually, I haven't ever read that too. Hmm. I'm not sure if it is another name for return instruction. I think you should try to find out what C3 instruction is. Maybe it is some x86 instruction, if it is a return instruction or not. But implementation depends on the number of C3 instructions in the machine type. But see, that is C3 register, I think, the page table base register. Yeah, so the instruction, I don't know. And okay, if I find anything, then I'll post it. But I cannot try to answer it also now because the assignment, I cannot answer questions from the current assignment. You can try to find out what is a C3 instruction. But I think it doesn't, just as a hint, I think it is doesn't depend. The answer doesn't depend on C3 instruction, how many C3 instructions are there or not. Like think about it. If you have a say 2 return instructions in your program, forget about C3 instruction. If you have 3 return instructions in your program, does the number of your gadgets is is the number of gadgets limited to 3, or can you form more gadgets? So it's just that how do you form gadgets? It's just a sequence of instruction ending in ret. Okay. So it think about it. I think the answer doesn't really depend on how many even how many red instructions are there in your program. Okay, so problem 8 here is match the following: Trojan horse, buffer overflow, and double free privileges to these three options. I'll give you some time to look at the options. Okay, any answers? Yeah, yeah. Yes, I think option D is correct. Trojan horse is malicious code, and overflow, buffer overflow is access data, corrupts values in the adjacent memory addresses, and double free is memory is freed more than once for a specific memory address. Yeah, so option D is correct here. Is there any doubt? Okay. Okay, the next one is here. Your project manager asks you to ensure that a particular source code is free from buffer overflow attacks. Which of the following would you need to look out for? Scanf in the code, strcpy in the code, for loops that manipulate arrays, and all of the above. Yeah, so which of the following can be used basically to um, mount a buffer overflow attack? Scanf, strcpy, for loops that manipulate arrays. Which one? Yeah. Hmm. Yeah. 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 Yes, that is right. So yeah, your answer is right. So all of these can cause buffer overflow attacks, and what you said is absolutely right. So scanf, if you the input string size is more than the buffer to which it is writing, then that causes a buffer overflow attack. Strcpy, if the source from where you're copying is longer than the destination buffer, then that causes a buffer overflow attack. And for the loops, if the loop iterations are more than the size of the array, and on every iteration, if you are just say writing to the next element in the array, then definitely you will write past the array size, and that is an array bound. You'll write beyond the array bounds, and that will also cause a overflow attack. That is also overflow basically. So all of these are different ways of uh, exploiting the vulnerabilities, buffer overflow vulnerabilities. So you need to basically look out for all of these and have bound checks, say in string copy and in the loops and all of these places you need to have the bound checks. For scanf, yeah. Uh, I think there is some mechanism to add the width for the, you can specify a field width, so how many characters can be read with scanf. Yeah, yeah. So there is maybe some other more secure alternatives of scanf also, which should be used in place of the normal scanf. Yeah. Okay. So the next one is arrange the following based on the order of the parameters, like based on the order the parameters are pushed onto the stack. So first one is return address, then function call parameters, previous frame pointers, local variables are allocated. So these are different parameters on the stack. It is asking in the order they are pushed on the stack. Like how is your stack arranged? It's important to know the arrangement of the stack to understand the attacks and also the defenses. Any answer? Okay, okay, it's okay. It's if you can you look at the slides here. Yeah. So when a function is called, at that time, first we push the parameters for that function. So you're calling this function here from main, right? So 1, 2, 3 are the parameters. So first we push the parameters for the function. After that, we are going to push the return address. So we called the function from here. And when the function finishes execution, we need to return to the next instruction in the sequence. So we push the return address here, which is here, and then we push the frame pointer, previous frame pointer here, to restore the stack when this function completes. And then after all of this, then we push the local variables of that function to which we have entered, like here buffer1, buffer2. These are local variables of this function. So then we are going to push the local variables here. So according to this here, we have here, if we look at the options, then first we are going to push the function call parameters. Then we push the return address, B, then A. After that, we push the previous frame pointers, and then in the end, we push the local variables. So that is option C. So it's the address of the stack pointer. It's a address of the previous stack pointer. Like now your stack pointer. So you want to be able to restore to the previous frame pointer. So when this function finishes execution, then you will have to pop all of these values, and then it will be, it here is a, it is like telling you where it was, where is the previous, from where the previous frame is starting. Yeah, like previous function call. Previously you were executing main, so where the main function is starting from, here, previous frame was starting from here. So when you were executing main, as part of main, you have pushed here the locals, then you called function, then you parameters, then return address, and then you push it here that now a new frame is started for next function. So you are putting here the starting address of the previous function frame. Oh, so for every function call, a new function record is added on the stack, right? So like main was called from some place. It's the first entry point to the when you execute a function, it's the first entry point. But so some maybe when your program was loaded and started executing, then some other process might have started this process. So that time it has initiated the stack. So when it initiated this stack, then it added parameters for main, because sometimes we give parameter to the function on call, right? We give parameters as these argc, argv. So those parameters are added here. Then the return address is where the main is going to return. That is the return address. And then here we are saying, okay, now the previous frame pointer for main, I think it would be maybe the starting address. But after that, here the main is starting. So when main function is started from here. So first we are putting here the locals of the main function, and then we put, so in the main, while the main is being executed, at that time the another function is called. So when another function is called, then we first put the parameters of that function, new function, then we put the return address, then we, because now we are going to start a new function, so we here record the previous frame pointer. Where was the previous function location was this? Because later we will have to pop all of these and reset our frame pointer to here. Now our frame pointer is pointing here. but later we will have to read this value and we will then reset the frame pointer here. So there are two pointers here. One is frame pointer versus stack pointer. The stack pointer is pointing to always the top of the stack where you are going to push the next value, which can be say local variable, and frame pointer is pointing to the location from where this frame is started. So for this function, the frame is started from here, from this location. Now when this function, when it finishes, there is nothing happening here. So let's say it just allocated two buffers and then it finishes. So then you will pop the locals of the function, they will be removed. Then this value will be read and the frame pointer will be set to this previous frame pointer. So frame pointer will now then point here, and your top of stack will then like go back. It will read, then it will read the return address here, and then these parameters for the function will also be popped back, and it will come back here. Stack pointer will come back here. So everything, yeah. Yes, yes, and previous frame pointer is stored here so that we can restore where the frame was earlier. So we always keep a, like this frame pointer is always pointing to the current frame, and whenever this frame is popped, whenever we a function is returned, at that time we are going to, like here, reset the value of frame pointer to the previous frame pointer here, and then previous, like that. Okay. Is there any other question? The Okay, so we have, yeah, so we have covered all the questions that I had for today. Today's quiz, it's option number C. Yeah. First, previous function call parameters are pushed, then return address is pushed, then previous frame pointer value, then after that local variables. It is as shown here in the slides. Yes. Okay. Okay. Thank you so much for attending. If you have any other previous questions, you mean from the last assignment? Oh, do you mean which week? Okay, can you? Yeah, yeah, you can paste that question. Hmm. 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 Okay. Okay. So order and scheduler, uh, so that means that in order to find which process to schedule next, if there are n processes in the ready queue, then it basically needs to check all of those n processes, and then it finds out which one is the one it want to execute next. So that will take more time. So that's why I think it is saying it is not scalable to large number of processes. If your processes are say n is 1,000 is still okay maybe, but if it is 10 to power 6 or something, then that's a lot of time. So we want something which is more something like say order of one scheduler, because then order of one scheduler means that the process then you do not, it takes only constant amount of time to decide which process to execute next. For that, you will need to have your ready queue arranged in some manner so that, say, the head of the ready queue is always pointing to the next process that you want to execute, maybe. And here it is suggesting that it has two run queues to prevent starvation. Exactly how it is saying, maybe one of the queues is say, uh, like I can give you maybe one example is that whenever in the shortest job first scheduling, you always need to find out the next process which is shortest, right? So if your ready queue is not arranged according to the shortest time, like the which process has the shortest burst time, then you will take say order n time to find out which process is has shortest burst time. That will be your option 1. But if you keep your ready queue arranged in sorted order, then it takes you only order one time to find out the next process which you want to execute. So has two run queues to prevent starvation. uh, to prevent starvation. Okay. Okay, okay. Okay, right, right. Yeah, every process got a chance to run once, at least once, before it gets a chance, like before others are executed. Uh, yeah, so basically what you're saying is that the completed queue, separating the queues in the completed queue and the processes which has to run, which have not run yet, you are giving the processor to every process at least once. Yeah. Mm, mm, but how does that still I think for option order of one scheduler, like let's see, sometimes the options they do match I think the best fit, no maybe not the exact fit to that, but let's say the next one is time slice of a process is set based on priority of the process. That can be done, like it can be done if you want to have, if you have a more higher priority process, then you can give more time to that process. And the last one is dynamic priority. Yeah, it can be varied, like not in your round robin, but there are variants of the like round robin and other like there are more complex scheduling algorithms which say as a process ages, then they increase the priority of that process also. So if a process has been there in the ready queue for a long time, then it increases the priority of the process so as to avoid say starvation. So in that similar manner, uh, if a process has higher priority, then you want that process to finish first. So maybe you will give infinite time slice to that process, saying that as long as this process doesn't finish, just keep executing that, because that process maybe is, say, related to your, say, processor heating, or some battery or something. So that process is very high priority. Okay, so this process needs to execute first, and maybe you can give it as much time as it needs, right? So the scheduling algorithms, they are not like what we have, right? They're very simplistic, but they more complex, and according to different goals like prevention of starvation or prevention of deadlock, etc., they can be modified. Yes, yeah. And then there is dynamic priority. So that is, I think, for starvation only. It is saying that is, then it is saying is based on average sleeping time. Average sleeping time is, I think, it is saying that if the process is maybe say requires IO more than compute power, then maybe you can have more priority for that process, because that process needs to run for a very short time, and then it is spending more time in IO. So you want to give it the CPU for, let's say it needs CPU only for 2 cycles, then you just give it the CPU, and then for 10 cycles maybe it is just doing IO. So you, so that the process keeps making progress, you just give it more priority, so that it comes, it runs, and then it goes back to I like doing IO. These this Yeah, dynamic priority just means that you change the priority based on, let's say, how much time the process is sleeping. Uh, it's like you are dynamically changing the priority of a process. It's not static. It's not like a process which was high priority in the big, which has a priority number, say 4 in the beginning, is always 4 priority. You're just changing it as on the behavior of the process. If process is, say, sleeping longer times, then maybe you will increase it priority. If it is sleeping, let's say, less time, then you decrease it priority. So sleeping more time means it is a IO bound process. That is, it is spending more time doing IO operation. And if it is sleeping less time, means it is a CPU bound process. It is spending more time doing computation on the CPU. Now, based on your policy, so when you design your scheduling, so it's what I'm saying is only one of the options. It's not like it is one of the scheduling policies which is already there, but based on what you, so we design scheduling policies, and then we evaluate them, right? We design a scheduling policy. Let's say that if the average sleeping time is more, then we are going to increase the priority, and then we take a number of processes and have with different various sleeping times and different CPU time, and then we run it according to our policy, and then we see, then we evaluate it on different parameters that we have read, right? Response time, turnaround time, etc., and then we see whether it is working efficiently or not. But what here it is saying, it's like open-ended only. It is not saying what priority is being given. It's just saying that dynamic priority you are assigning to the process based on average sleeping time. So here option C you're saying is the right one, like has been the right answer. Do you think any other option is also correct? Yeah. Okay. Right. Yeah, I mean, yes, um, that's true. But sleeping time is indirectly, no, like when we say average sleeping time, does it not indirectly mean that it is, if the sleeping time is say zero, it means it is always CPU, it is always it has no IO basically. And if it is having more sleeping time, it means it has less CPU requirement. You can indirectly infer that, no? Yeah. Hmm. Hmm. Yeah. Let me just copy it. Okay. Okay. Okay, so there are three processes arriving at time zero with total execution time of 40, 50, 60 milliseconds respectively. Each process spends 40% of the execution time doing IO operation and next 60% of the time for computation. The scheduler uses first come first serve scheduling, assuming that all IO operations are overlapped. How much time in milliseconds the CPU is idle? Uh, okay, so here 40%, right? It is saying that is 40 milliseconds. Yeah, and then the time that it is going to execute, the burst time is 40 minus 16, which is 24 milliseconds. And then for the next process, 50 into zero point 0.4 is 20 milliseconds, and the burst time is equal to 30 milliseconds. And the next one is 60 into zero point 0.4, which is 24 milliseconds, and burst time is equal to 26, 36, 36 milliseconds. Okay, so the first 16, 20, so it the first process is spending 16 milliseconds. So it is saying from the question's language, it is like saying that the first 40% of execution time. So every process is doing IO initially and then for 40% execution time, and then they are doing computation for 60% next. So that means process 1 will do IO for 16 milliseconds, then it will run for 24 milliseconds. So and all of these IOs are overlapped. So it starts executing at 0, means it from 0 to 16 millisecond, it is going to do IO. And similarly, P2 does IO from 0 to 20, and it does from 0 to 24. So then if in this manner, that means P1 will come in the queue first because it finishes the IO first, then P2 will come in the queue, and then P3 will come in the queue. Okay, right? P Yeah, yeah. All IOs are starting at the same time and they are overlapped also. So that means they can do IO simultaneously, all of them. So P1 is doing IO from 0 to 16, P2 is doing from 0 to 20, and P3 is doing from 0 to 24. So then P1 comes in the ready queue first. Okay, so ready queue in P1 will come first and then it will be scheduled. So then it will run from 16. It will start running from 16 milliseconds. Okay, because first 16 milliseconds from 0 till the end of 15th millisecond, it will do IO. On the beginning of 16th millisecond, it is going to, like for first 16 milliseconds, let's say, like it is doing IO, and then it is going to start the uh, IO, or sorry, compute. Is that clear? Yes. Yeah, yeah, yeah. IO and compute. So IO P1, I need to, I'll just remove. P1 will do the IO from 0 to 16, and then it will move to compute. Then it will do compute from 16 till 40. Its total time. Okay, and then on the simultaneously P2 is also doing IO from 0 to 20, and then it becomes available, it becomes ready in, so when so then it becomes ready here. P1 has been removed from the ready queue. Okay, so initially in the ready queue there was no process because everyone is doing IO. On timestamp 16, P1 becomes available in the ready queue because it finishes its IO, and then we move it to compute. So it starts executing here. Okay. Then P2 finishes its execution at timestamp 20 and it comes in the ready queue. At, at the same time, P3 was also executing and it will execute till 24, and after 24 it also becomes ready. So at timestamp 24, P2 and P3 are in the ready queue waiting for their chance to execute on CPU while P1 is executing right now and it finishes at 40. So as soon as it finishes on 40, P2 will be removed from ready queue, moved to the compute, and it starts executing from 40, and it will execute from 40 plus 30. Okay, because its burst time is 30. So it will execute from 40 till 70. At 70, it executes, it finishes its execution, it is removed. Then P3 is there in the ready queue. P3 will be brought here to CPU and it will start executing, and then it will run from 70 to 106 milliseconds because its burst time is 36. Okay, so in entire here, if you see, the CPU is busy all time. Okay, from 16 till the end. Only the first 16 milliseconds it was idle. From 0 to 16 it was idle because there was no process to run. Okay, now this question was like, um, Like it, if it were, so in the beginning only it was idle. If it was, if it had so happened that maybe P3 had a very high IO and it was not available until P2 finishes execution, then there would be some idle time in between also. There can be some idle time in between also, but in this question, there is idle time only in the beginning. But after that, the CPU is always busy. Okay? Okay. Yeah, yeah. Yeah, yeah, no problem. Hmm. Yeah. Lock. So there is some variables a lock, and so the lock will be atomic. So only one process can take the lock at a time. It's not possible. So when is deadlock possible? Deadlock is possible when, say, there are two variables involved in taking the access to the critical section. So if there are two locks, then one of the process takes lock 1, other process take lock 2, and now both are deadlocked because in order to enter the critical section, you need both of the locks, say. So that is like a deadlock situation, an example of a deadlock situation. Yeah, so here yeah, go ahead. Yeah, so the exchange instruction is only ensuring that uh, only one process, only it's only ensuring that the lock is a process gets that the instruction first is atomic, that it executes, right? Atomic means that either it executes completely or not at all. It doesn't leave any effect partially. So either a lock will be taken by a process or not at all. So it ensures that access entry to the critical section is deadlock free. But what is starvation? Starvation means if there are three processes different. Yeah, since starvation is different. Okay, you were saying something. Do you want to continue? Yes, yes, yes. So, but exchange instruction itself cannot ensure that, because exchange instruction is only a, it's like you exchange the value of lock with true or false, like you take the lock or not take the lock, right? You're just taking the lock. It is not this instruction itself cannot ensure like which process is entering. Any process which executes the instruction first will get the lock and enter the critical section. But if a process, every time there is a process which is starved, like it is not able to get the lock, so it is not maintaining any queue, right? It is not maintaining any queue where it is saying that, okay, if a process has waited for a long time, then let us give lock to that process. There is no mechanism like that to ensure starvation free. Yeah, because there is no queue like that. Yes, yeah, yes, yeah, sure. Okay. Hmm. Yeah, 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 I can see. So first one is max allocated and this is allocated. Maximum you can allocate. Hmm. 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 Yeah. Hmm. Hmm. Okay. Okay. Okay, so here you have, these are the processes. This is the maximum that the process need for to be allocated, and this is the currently allocated to each process, and you have the maximum count of the resources here. So the max count of the resource is 1057, but you have already allocated some resources to the processes here. So then you need to find first the available resources now, right? So available, sorry, the spelling mistake. So available will be 10 minus 2 plus 3 plus 5, which is 7, comma 5 minus 1 plus 1, 2, and 7 minus 5, which is 3, 3, 2. So 332 resource units are available for a resource ABC. Okay, now the answer here is, I'll just verify the answer. Okay, we can just verify the answer here. So it says that first let us allocate to P1. So we allocate to P1. So if we allocate to P1 3, we have 332 resources available. So we can allocate 3 units. Sorry, 3, it needs 3. 2 has already been allocated, right? So 1 is sufficient. So we give 1 to this. Then it needs 2 here. So we give 2 more. 2 from here. And then it needs 2. So we can give 2. So so that means we can give resources to P1 completely. So P1 will finish execution. If we give it resources, it will finish execution. So then these two resources will become free. So when these two resources become free, our now available will change to, I'll just keep writing here only, P1 executed, right, P1 executed, and then it becomes 532. Then P3, it says, so 3 resources were available of the resource 1 with us. We had 1, yeah, 1 we gave. Yeah, 1 we gave. We gave 2 units of resource B, we gave 2 units of resource C. Then this process resource requirement is fulfilled, so it will finish execution. When it finishes execution, it will release all the resources back. So it will release the 2 units which of resource C we gave, 2 units of resource B we gave, and 1 unit of resource A which we gave. Also, it will release the 2 units of resource A which it had earlier. So 2 more resource units will be received. So we have added 2 here. So now available resources are 532. Now if we look at this, then we can execute only P3. We cannot execute P0, P2 or P4 because P4 needs 3 resource units of C. We have only 2. P1, P0 needs 7 units of A. We have only 5. P2 needs 9 units. We have only 5. So we can execute P3. So we will give units to P3. It has 2 units. It needed 2. So we don't need to give resource A. It needs 2 units of resource B. It already has 1. So we need to give 1 more. And then it has 1 unit of C and we need to give it 1 more. In that manner, basically we can satisfy the resource requirement, and once the resource requirement is fulfilled, then it will execute and finish execution, and then it will release the resources. So now when it finishes its execution, it will release the resources which it had occupied earlier, these. So we get back these resources. So when we get back these resources, it will become 5 plus 2, 7, 3 plus 1, 4, and 2 plus 1, 3. Okay, so now I'll just mark them that they are done. Now with these resources 7, 4, 3, can we do P0? No, because no, can we do P0? Yeah, we can do P0. We can do P0 because it has, its requirement is 743 only. And we can do P, can we do this? It requires 9 minus 3, 6, 0, and 0. Yeah, we can do P2 also actually now. And yeah, and P4 is 4. Yeah, 4, 3, and 1. So we can do P4 also. So we can do them in any order now, basically. Yeah, but initially we need to start from P1 only. We cannot start from P2 because P2's requirement is this 9, which we cannot satisfy initially. So we need to start from P1 and P3, and after that, this can be any order. All 3 factorial permutations, 6, 6 uh, can come here. Basically, 6 schedules are possible now. Because P1 and P3 are fixed, but after that you can have 6 possibilities here. So those 6 possibilities, any of them is possible. Okay? Yeah, yeah. Because second one is saying P2 is executed first, but we can't execute P2 because it needs 6 resources initially. We have only 3. It needs 6 units of resource A. We have only 3 available in the beginning. Okay, okay, okay. Yeah. Uh, yeah, yeah, please continue. Okay. Uh, Actually, I am not very sure about the dining philosopher's problem. I think I'll have to look at it. Yeah. But here, I think Srinivas has said that something. Can you elaborate, Srinivas? He's saying that 5 is sufficient for synchronization problem, but not for deadlock prevention. Mm, No, but so synchronization and deadlock, I think, are different. So synchronization would just mean that you say there is a critical section. You do not want the processes to access it simultaneously, because if they do, then they will corrupt the data. There is race conditions. But deadlock, it is possible that none of them is able to enter the critical section due to deadlock. That is achieving the property of mutual exclusion still, right? It is achieving mutual exclusion. No two processes are in the critical section at the same time, but there is a deadlock. Yeah, yeah. Um, mm, yeah, this is a, yeah, I understand. It is a classical problem. It is a number of words. Okay. Um, okay, can you just like for now I don't have the answer, but can you please put this question on the forum and I'll try to get back to you uh, today or tomorrow because like I'll get back to you why what the correct answer is if it is not if you and you can also add your solution there with the question about the monitors and let us look at it. Right. Yeah, let us look at it. Uh, Please post it and then I will try to answer it. I um do you get Google Forum messages on your mail? So you can just go to one of them. Okay. Yeah. Okay. Yeah. Uh, sure. Yeah. Sure. You can send this to me also, or you can write, or you can post it on the forum also. I'll try to answer, or you can write it to me. Okay. Okay. I'll just stop the recording. Sorry. Thank you so much.